Hi, this is Bill Reese, and we're going to look at the spreadsheet that is titled Two Risky Assets. Now, there's going to be no risk-free asset in this particular spreadsheet, just two risky assets, X and Y. And of course, our definition of a risky asset is it has some positive standard deviation. A standard deviation of zero means you are risk-free. So let me do the screen share with this particular spreadsheet, and we will see what it is telling us and how to work with it here. Okay. So this area in here, okay, is all called, it has expected return on the y-axis, standard deviation on the x-axis. This is all what we call mean variance space. Now, it's called mean variance space, even though this is not the mean, it's the expected return, and this is not the variance, it is the standard deviation. But hey, I'm not the one who titled it, but that's what it's called, mean variance space. And what we're going to be doing is mean variance analysis, which you can see is right up there at the top. So for right now, just for a second, ignore this line here, but take a look at the end of the line where we have X, and at the end of the line over here where we have Y. Well, that is where X and Y lie in mean variance space. We have set this up so that the expected return of X, we'll just say it's stock X, is 10%. The expected return of stock Y is 20%. There you can see the expected return of Y is 20, the expected return of X is 10. The standard deviation of stock X is 7%. You can see right there, it's 7%. The standard deviation of stock Y is 10%. You can see right there, there's the standard deviation of Y is 10%. We're going to leave those at those values. The variance is always going to be the standard deviation squared. So there's the variance of X, there's the variance of Y. Now we're going to say right now that the correlation between X and Y is 1. Now, you'll never see that with two naturally occurring assets. Okay, that means these two assets move perfectly up and down together all the time. It never happens. Now, you can create derivative assets that are perfectly positively correlated with a naturally occurring asset, but you won't see, for example, Nike and Home Depot that move exactly perfectly together all the time. But we want to see what are the implications of that here. Okay. So and we're going to be changing that around. So the covariance between X and Y, as you know, is the correlation between these two assets right there, multiplied by the standard deviation of X times the standard deviation of Y. So the correlation between X and Y times the standard deviation of X times the standard deviation of Y equals the covariance between X and Y. Covariance and correlation measure the exact same thing, measures the degree to which they move up and down together or they move up and down opposite each other. They just use different units, okay? Just kind of like measuring minutes and hours, both measure time, okay? But they use different units. So what we've got here is we've got a whole bunch of different possible weights on X down here, all the way from 0 weight on X to 100% of our money into X. And the weight on Y is always going to be 1 minus the weight on X, right? Our money, whatever doesn't go into X has to go into Y. And then let's pick this one, for example. If half our money is in X, that means half of our money is going to be in Y. And the expected return on the portfolio, as you can see right here, is going to be the weight on X times the expected return on X plus the weight on Y times the expected return on Y. That's what we've got right there. So for any of these here in column D, that when we change the weight on X, it automatically changes the weight on Y, and it will tell us what is the standard, what is the expected return on that particular, those particular weightings. Standard deviation of this portfolio is going to be the square root of the variance of the portfolio. And this is our variance of the portfolio. This is going to be the, and I may not get these in the right order, so it's going to be the weighting on X squared times the variance of X plus the weighting on Y squared times the variance of Y plus 2 times the weighting on X times the weighting on Y times the covariance between X and Y. So that is our formula for the variance of a portfolio that has two assets in it, and then the square root It gives us the standard deviation of that portfolio. And so as we see all of these different values here, it's just going to be with different weightings on X and Y. What is the standard deviation of the portfolio? So what is being plotted here, now we can look at the line, what is being plotted on this line is all the different combinations of X and Y. The one we looked at right here with 50% of my money in X and 50% of my money in Y is right there. Okay, half my money is in X, half my money is in Y. The expected return on the portfolio is 15%. The standard deviation on the portfolio is going to be, as we see, 8.5%. Now, we would say that we have no benefit of diversification here because the standard deviation of the portfolio is always going to be a weighted average of the standard deviations of X and the standard deviation of Y. Okay, so in this example, 0.5 times the standard deviation of X plus 0.5 times the standard deviation of Y gives us 8.5%. The advantage of diversification is going to be when the correlation between X and Y is less than 1. When the correlation of X and Y is less than 1, when they're not perfectly positively correlated, which you're never really going to see with two naturally occurring assets that they are. So when they're not perfectly positively correlated, we're going to see that it has no effect on the portfolio's expected return, but it will have an effect on the portfolio's standard deviation. So let's change the correlation from 1 to 0.5. Okay, so let's make the correlation here equal to 0.5. Okay, we'll do that. And we see now we have got a bend. Okay, in this, it's got a curve to it, and it is the geometric shape of a hyperbola. And so what we've done here is and if you noticed, the expected returns did not change at all because all of these expected returns don't involve correlation. Okay, but the standard deviations did change because they do involve the correlation, because the correlation determines the covariance, and the covariance is in there on cell C8, okay, which is going to be right here in each one of those, okay? So what we've got there is when we're reducing this correlation, it's going to reduce the standard deviation of the portfolio, and that's why you've got that bending going to the left there, you can see. Let's suppose that our correlation isn't 0.5. Suppose our correlation between X and Y is even lower than that. Suppose it is 0. I'll type in a 0 there, and we see there is even more of a bend. The lower the correlation between the two assets, the lower is going to be the standard deviation of the portfolio. And the expected returns, it still hasn't changed at all there. Now, there's nothing magical about a correlation of 0, okay? It's not like, oh, that's a special number. It's just the midpoint between +1 and -1. We can get the correlation even lower than that. If X and Y tend to move opposite each other, but not perfectly opposite each other, suppose their correlation is going to be -0.5. Okay, so we type that in there, -0.5, and we see even more of a bend. Okay, we've got a lower standard deviation for each of the combinations of X and Y, where you've got some weight in X and some weight in Y. So take a look again where half of our money is in X and half of our money is in Y. It's still got a 15% expected return, but if you remember, when X and Y move perfectly together, the standard deviation of the portfolio was 8.5%. Now it's 4.44%. That's significant because remember, investors are risk averse, which means they want lower standard deviations to their portfolio. So an investor likes this better than they do when X and Y were perfectly positively correlated at 1. So the lower the correlation, the more this hyperbola is going to bend to the left, which is something that risk-averse investors like. All right, well, let's see how far we can go in this particular situation. Can we go all the way to the left? Yeah, we can, as a matter of fact. If the correlation between X and Y is -1, meaning that they're perfectly negatively correlated, they move exactly opposite each other all the time, then in that situation, well, what we've got is we no longer have a hyperbola. We have two straight lines that intersect on the y-axis. And I've already set this up so that the weights are in here to be able to get that intersection there. And it's right here when we've got 58.82% of our money in X, 41.18% of our money in Y. The standard deviation of the portfolio is 14.12. I'm sorry, the expected return on the portfolio is 14.12%. It's still just a weighted average of their expected returns, but significantly, the standard deviation of the portfolio is 0. Okay. We now have a risk-free portfolio. This is an important concept, okay, in risk management. If you have an asset, let's just say it's asset Y that is risky, goes up and down, right? Y is risky, it's got a standard deviation of 10%. And you are concerned about that risk. The way you get rid of that risk is you combine that risky asset with another risky asset that moves exactly opposite to it. And as it moves exactly opposite to it, when you have the two of them together in a portfolio, you've actually eliminated the risk in that situation. So that's what derivative assets do. Again, you're not going to find, let's say, two stocks that move exactly opposite each other, but you can create options. You can create futures contracts, forward contracts, swaps, insurance contracts that move exactly opposite to a naturally occurring asset to totally get rid of the standard deviation, gets rid of the risk. And as you can see, it doesn't mean the expected return goes down to 0. In this particular case, the expected return is quite high at 14.12% that you've got. Now, in the real world, you're probably not going to get an expected return as high as 14.12% when you combine two assets and get rid of the risk between them, because that would be arbitraged away. Everybody would want to do that because that's a huge return with 0 risk associated with it. But the point that we're seeing here is that as the correlation is lower between these two risky assets, then in mean variance space that we get this hyperbola that has a bigger and bigger curve to it, and it's going to the left. And in fact, if X and Y, these two risky assets, are perfectly negatively correlated with the right combination of the X and Y, you can create a risk-free portfolio. Let's take this back for a second let's just say point 2. Point 2 is the correlation. Okay, so they're not perfectly positively correlated. They're positively correlated, but they don't move exactly together. Okay, and let's suppose we want to say in this case, all right, where is the minimum variance portfolio here? In other words, what point on here is as far to the left as we can go? Now, we could look at this and kind of make a guess as to where it is. And I'd say, it's probably somewhere around here. What is the weight on X and the weight on Y? I don't know exactly where it is. I could look on here and I'd say, okay, where's the smallest number? And it looks like it's maybe about right there, 6.24%, when I've got 70% of my money in X and 30% of my money in Y. But if we want to find out, and that's probably pretty close to it, but if I want to find out exactly, we can do that with Solver. So we go to Data, okay, and we go to Solver, and we say what we want to do is we want to get, I'm going to go right down here, choose this particular standard deviation, because that's the one that's closest to it already, that I want that cell to be minimized. And I want to minimize it by changing the weight on X right over here. Okay, so I'm going to change the weight on X, which will, as we know, change automatically the weight on Y. So I'm telling Solver, hey, make the weight on X such that the standard deviation of this portfolio is as low as it can possibly be. So I hit solve, and we've got a solution here. And the solution is, it was pretty close to 70%. We knew it would be. It's 71.07%. And this still says 6.24%, but if you took it out more decimals, we'd see that it's actually a little bit lower than it was before. So when you put 71.07% of your money in X, and to be more specific, it's 71.0743801, et cetera. Okay, and 28.93% of your money in Y, you've got an expected return of 12.89% and a standard deviation of 6.24%. And with this particular X and Y and this particular correlation between them of 0.2, that is the minimum variance portfolio. Now, if I change the correlation between X and Y, I'd have to redo it all over again to find the minimum variance portfolio. It's not always going to be 71% of my money in X and 29% approximately into Y. Okay, so we have seen how changing the correlation between these two risky assets changes the shape of that hyperbola. That when the correlation is 1, it's actually a straight line. It's not a hyperbola. When the correlation is -1, it's two straight lines. Okay, and there is a combination of X and Y that gives us a zero standard deviation. And when the correlation is somewhere between +1 and -1, for example, 0.2 here, then I've got this nice hyperbola shape. So play around with this particular spreadsheet so that you become comfortable with it and you understand a little bit better what goes on when we've got two risky assets here.